Okay, we've got some more acid stuff here. So I've made this table, and it's just a piece of a full-page table in my textbook, and you probably have something like it. I want you to notice something. I'll use my yellow arrow here. Hopefully it comes out on your thing. The arrow I just drew, going from the bottom to the top, goes to the strongest acids on the top. You could tell that from the Ka value. When I say large, I essentially mean infinity. That means that the molecule completely dissociates and gives two pieces, basically an H plus or H3O plus and a ClO4 minus. Completely dissociates. So the Ka is basically infinity. And you see that for two of these acids here, nitric acid and perchloric acid. Something you'll learn a little later is notice how there are far more oxygens than H's. So here this has 3 extra, this has 2 extra, and that's usually an indication of a strong acid. The base that it's associated with, or its conjugate base, notice the difference. You're missing an H. So this perchlorate and the nitrate ions are the conjugate bases that are incredibly, incredibly weak. So if this is infinity, these numbers are essentially 0. They don't act as bases at all. And if you remember from first semester, you might even notice that these are spectators. They never form a precipitate. So they're kind of boring things. Look at the other list I provided for you here. All of these molecules are, almost all, are neutral molecules. I do have one here which is an ion. That's an important one called ammonium. But each of these only partially dissociates. And the way you could tell that is to look at the Ka's. They range from fairly small, 4.0 times 10 to the minus 10. Did I get that right? And all the way up to sulfurous acid, which is 1.2 times 10 to the minus 2. Now, what's common to all of these is that, again, even though that's a pretty large range of numbers, they're still considered all weak. They're weak because they only partially dissociate. This is a Ka expression, so you've got the full acid on the bottom breaking up into its two pieces. If these numbers are very small, it means that you don't have very much of the numerator, but you have a lot of the denominator. Notice how there's an inverse relationship with the Kb values. So if you look at the conjugate bases, that's basically the same molecule or ion missing an H. So you see HF, F minus, HCN, CN minus. In each of these cases, these guys can act as bases, and notice that they get relatively strong. So what was a list of strong acids at the top and weak acids at the bottom, now you see that this is the strongest base for the CN minus, and the weakest is up at the top. When you say a base molecule, you mean that base, remember from my previous slide, or my previous video, is that a base will steal an H from water to become Hb plus OH minus. Something is really interesting. If you take the two numbers for an acid-base conjugate pair and multiply them together, you get 1.0 times 10 to the minus 14. That's exactly what we call the Kw. The Kw is the equilibrium constant of a water molecule reacting with another water molecule to give H3O plus and OH minus, which is kind of interesting. pH is minus the base 10 log of H3O plus. pOH is minus the base 10 log of OH minus. We'll get to more of those as we go on. Let's do some problems here. Write the formula and give the name of the conjugate base of each of the following acids. So what's conjugate base again? It's the molecule after it gives up an H plus. So here I have 3 different conjugate bases. And the names you should know are from first semester. So you have the cyanide ion, the sulfate ion, the fluoride ion. You may have to memorize those. You can make some index cards. You'll do fine. Write the formula and give the name of the conjugate acid of each of the following. So that means you're adding, so this was minus an H plus. This is add an H plus. So the conjugate acid is NH4 plus. This is H2CO3. This is HBr. This is called hydrobromic acid. This is carbonic acid. This is the ammonium ion. What are the products? Indicate the conjugates. So all of these guys are acting as acids. So if they act as acids, they're going to give up an H+. So I'm going to have an NO3 minus plus H3O plus. This is going to be SO4 2 minus plus H3O plus. Oops. This is acting as an acid, so it's going to become H2O plus HF. Okay, so the three underlined things are all acting as acids. The thing you might notice then is these are acting as bases. They are accepting a proton. Write balance reactions showing how HC2O4 minus can be both an acid and a base. Let's do the acid first. So that's when you give up a proton. So this guy is going to react with water, and it's going to give up an H plus to create H3O plus, and then the guy is left over. Make sure your charges work out. Remember, you're giving up, give up an H plus. Now we're going to accept an H plus. So I'm starting with the same molecule. It's going to react with water, but now it's going to accept an H plus to become a neutral molecule plus OH minus. So this is what my book calls amphoteric or amphiprotic. It can give up an H or accept an H. In the top one, it's acting as an acid. In the bottom one, it's acting as a base. What is the pH of a 0.0075 molar solution of HCl? When you see that something is a strong acid, it means that it totally dissociates. I really could have put water there and put H3O plus instead. The definition of pH, it's minus the log of the H3O plus concentration as a molarity. So it's minus the log of 0.0075 molar. I know that that's that number because it totally dissociates. Actually, Daddy made an error there because this really should be a straight arrow. It's not an equilibrium. So we'll get to some weaker acids on another day that so this gives me 2.12. That's a very acidic pH. If you look at a number line, 7 is in the middle. The high number side of 7 is a base. The low number side of 7 is an acid. So this is clearly an acid. What's the pH of a 1.2 molar solution of KOH, a strong base? Strong base means that it totally dissociates into K plus and OH minus. So I think the best way to do this is actually calculate something different first and then make a quick conversion. The POH is minus the log of the HO minus concentration. So I'm going to do this. 1.2 times 10 to the minus 4. I do the log. I get rid of the minus sign. I get 3.92. And the pH is going to be equal to 14 minus the POH. So for us, that's going to be 10.08 for the pH. And notice that that's very, very basic, whereas the other one was very acidic. Finally, I've got 3 different equilibria on my slide. And the question is, which of these is the strongest acid and which one's the weakest acid? For this one, you want to look at the Ka values. Notice that this one is the largest. That means that the numerator, or the product side, is the greatest of the 3. So that means out of these 3 acids, this one gives up H plus easiest. It has the largest Ka. The weakest acid is the one with the smallest Ka. So that's going to be HPO42 minus. The smallest Ka. What's the conjugate base of HF? Well, when HF reacts with water and it acts as an acid, this is the conjugate base. It's the same molecule missing an H+, and that's how you get an F-. What's the weakest conjugate base? The thing you need to remember is that if you have a stronger acid, then it's a weaker base. I told you that from the other slide. So if I have the strongest acid is the HF, then the F minus is the weakest base. What's the strongest conjugate base? That's the one with the weaker acid. So the weakest acid is HPO42 minus, so that means that the PO43 minus is the strongest base. All right, I hope this helps, and I'll call you soon. Bye.